Today I'd like to talk with you about what happens when bone fractures and how do fractures begin. A magnified view of bone taken with the atomic force microscope by Johannes Kind in my lab shows there are all these rope-like things, these rough-looking rope-like things. What those are is mineralized collagen fibrils. Organic fibrils coated with mineral particles, and they have mineral particles inside them. We can remove the coating of mineral particles as shown in the green insert, and then you see the banded nature of the collagen fibrils. These collagen fibrils are the same kinds that are in skin and other body tissues, but in bone they're mineralized with these plates to make the bone stiff and able to resist compressive loads and resist fracture. But let's ask where bone fractures begin. In order to do that, we need to first look at the structure of bone. Now, bone is what's called a hierarchically ordered material. Now, what that big word phrase means is that bone has structure on all different length scales. So if you look on the length scale of 1 meter, then you see that bone is very complex, right? There's all these different bones, the finger bones and the arm bones and all that kind of stuff. And as you start looking at more and more magnified scales, you see that the differences in bone persist. There's cortical bone that's like in the outside of your bone, and trabecular bone that's like in the inside of vertebrae. And we look more and more magnified. And the top row shows the range of bone that's been well studied by current technology. There are many techniques that can look at bone at these length scales. There's optical microscopy, there's X-ray, there's computed tomography. Many techniques can look at bone at these length scales, and bone is, I would say, very, very well understood on these length scales. Where it gets tricky is when you go below these length scales and you go down to the bottom row. Here it's been very hard to study bone because the mineral plates in bone, for instance, are just a few atoms thick. They're very, very tiny, and so it's taken very powerful microscopes, atomic force microscopes, to be able to look at them for the first time. And what you see there at the 1 micron scale is a picture of these mineralized collagen fibrils that you saw on the Physics Today cover that are sticking together there. And in the next frame, you see what you would imagine. See, these are more or less rounded fibrils, and so imagine what the cross-section of that would look like. You see the rounded fibrils coated with the mineral plates, and in between them there's something. And what is that? It's a liquid gel. Your bone has these fibrils inside a liquid gel, and it's the liquid gel that holds them together. Now, as you go down to finer and finer length scales, bone becomes well understood again. By the time you get down to the last one, down at the 1 nanometer scale, and you're looking at individual atoms and molecules in the bone, there are very good techniques involving biochemistry and X-ray diffraction and so on for studying bone down at those length scales. But it's this intermediate length scale, around 1 micron, that's been very difficult to study bone. And unfortunately, that turns out to be the most important region. If we ask, where does bone fracture begin? What this slide shows is that bone fracture begins with the separation of mineralized collagen fibrils. This is what happens. So you've got these mineralized collagen fibrils that are held together by this gel, and when the bone starts to fracture, these pull apart. That's the beginning of bone fracture, and inhibiting that is inhibiting bone fracture. So we ask, okay, bone fracture begins with these things separating. What stops them from separating in healthy bone? So the next slide asks that question. It's a Nature Materials cover in which we gave what we believed was the answer. The glue within our bones resists the separation of mineralized collagen fibrils. We have high magnification images showing these mineralized fibrils that have been pulled apart during bone fracture, and what you can see is these little filaments of glue running between them. Now, these are scanning electron microscope pictures for which the bone had to be dried, and so that aqueous gel has evaporated, and what's left is the remnants of it in the form of these glue filaments between the mineralized fibrils. In the wet bone, in the fully wet bone, we would imagine it's just this gel with all these molecules running through the gel. And it's those gel molecules that contain sacrificial bonds and hidden length and that resist the fracture of bone. The glue within our bones appears to resist this separation of mineralized collagen fibrils. The mineralized collagen fibrils are held together by that glue, and as they get separated, in these very high magnification images that appeared for the first time in that magazine article, it was possible for the first time to see this glue, to see the remnants of that glue in the form of these filaments going between the mineralized collagen fibrils. Now these were scanning electron microscope images, and so we had to dry the samples to do these, and most of the water in that gel left, and we're just left with remnants of the molecules. In actual bone, we believe that there would be the gel there with the molecules running through them, holding this together. So bone is a very interesting composite, isn't it? We're used to composites like glass fibers in epoxy, or carbon fibers in epoxy, or glass fibers in some other polymers. These are the conventional fiber composites that we're used to. Bone is a very interesting one because the matrix that the fibers are in is a gel. It's very interesting. That's partly why bone is so supple and flexible and why bone can bend without breaking. But it's also an area that we can look to improve. How can we improve the properties of that gel? How can we inhibit the beginning of bone fracture by strengthening the glue? What can we do to strengthen that glue? What can we eat to strengthen the glue? What drugs can be taken? What exercises can we do? What can we do to stop bone fracture? Thanks.